In this video, we will talk through some of the relevant ideas that we need to consider when we're looking at completely factoring polynomials. We'll look at zeros and their multiplicities. We'll look at complex zeros and a special property of complex zeros. And then we'll talk about linear and quadratic factors of polynomials. So first, let's consider the factored polynomial p of x equals x minus 1 to the fourth times x plus 2 cubed times x minus I squared times x plus I squared. If I asked you how many zeros this polynomial has, what would you say? Would you say 4? Because if you said 4, you're partially right. If you said 11, you'd be exactly right. And here's the difference. We have this 0, x minus 1, is of multiplicity 4, so we need to count it 4 times. Similarly, x plus 2 is of multiplicity 3, x minus I is of multiplicity 2, and x plus I is of multiplicity 2. If we count all of the zeros of some multiplicity, then we can add up to the actual degree of the polynomial. And this is a special theorem that we have. This is the zeros theorem, which says every polynomial of degree n greater than or equal to 1 has exactly n zeros, provided the zero of multiplicity k is counted k times. So if we go back, this is actually, if we expanded this out, this is actually a polynomial of degree 4 plus 3 plus 2 plus 2, which is 11. Although it only has, quote, 4 zeros, we need to count each one its multiplicity. And then we can add up to have exactly the degree of the polynomial. So next, consider the polynomial p of x equals 3x to the fifth plus 24x cubed plus 48x. Let's factor this. If we wanted to factor this, kind of the obvious first step is to factor out the 3x. So we have 3x and then x to the fourth plus 8x squared plus 16. We could factor that into x squared plus 4 squared. Essentially, it looks like a quadratic. It kind of takes the form of a quadratic, so we can factor it similar to how we would factor a quadratic. Then, of course, if we factored x squared plus 4, we would have x equals 2i and x equals negative 2i. So then we have the zeros, and I'll add the extra parentheses. We have x plus 2i and x minus 2i squared. So altogether we have 3x times x plus 2i squared times x minus 2i squared. And I think at this point maybe you're starting to notice that every time the imaginary parts of complex numbers come into play, we have two factors to have the complex part. This is a special property of the complex numbers. This is the complex zeros theorem. If the polynomial p has real coefficients and that the complex number z is a zero of p, then its complex conjugate, z bar, is also a zero of p. So remember that the complex number z we might define as a plus bi, and then z bar is its complex conjugate, a minus bi. And if we go back up, you can see here we are. We have, if we say z equals 0 plus 2i, then its complex conjugate, z bar, is 0 minus 2i, and we have both of those as factors of this polynomial. In fact, each one is a multiplicity 2. So whenever we have one complex zero, we will always have another complex zero in the conjugate form of whatever one we found first. So that's the complex zeros theorem. And lastly, let's take a look at the polynomial p of x equals x to the fourth plus 2x squared minus 8. Let's factor this. So fortunately, this one is another relatively easy one to factor. I chose these on purpose so we wouldn't have to do the whole rational roots theorem and Descartes' rule of signs and remainder theorem and et cetera and so forth. But this one could easily be factored into x squared plus 4 and x squared minus 2. Now at this point we have a choice. We can either use the complex numbers to factor x squared plus 4, or we could not. So if we say we're not going to use the complex numbers, then we have to leave this as x squared plus 4. But we can factor x squared minus 2 into x minus the square root of 2 and x plus the square root of 2. So we've seen that a polynomial factors completely into linear factors if we use the complex numbers. However, if we choose not to use the complex numbers, then a polynomial with real coefficients can always be factored into linear and quadratic factors. Right? That is, at the very bare minimum, we might end up with something that looks like this. That might be the biggest thing that we have, and that would be called one of the quadratic factors. Our other two here are our linear factors, as we've explored in depth up to this point. The linear and quadratic factors theorem. Every polynomial with real coefficients can be factored into product of linear and irreducible quadratic factors with real coefficients. That is, irreducible in the sense that we're not using the complex numbers. This is particularly useful when we get into partial fractions, so just kind of keep this in the back of your head. But for now, we'll generally be completely factoring in any given polynomial. So in this video, we looked at the linear and quadratic factors theorem, we looked at the complex zeros theorem, and the zeros theorem. The zeros theorem says that for every polynomial of degree n greater than or equal to 1, that polynomial has exactly n zeros, provided that you're counting multiplicity. The complex zeros theorem says that if we have a complex zero z, then we also have its complex conjugate z bar as a zero of any given polynomial. And then with the linear and quadratic factors theorem, we can factor over the real numbers into a product of linear and irreducible quadratic factors with real coefficients.